Let's now look at the integrator circuit in the frequency domain. Noting that Z sub C for a capacitor, Z sub C is equal to 1 over Cs, we can then write the transfer function T of S, which is just equal to V out of S over V in of S, is then equal to negative, the impedance in the feedback is Z sub C, divided by the impedance in the tied to the source, which is just R, and we get then that the impedance of the capacitor is 1 over Cs over R, or we get then that the transfer function is equal to 1 over R times C times S. Now, if we let S equal j omega, then we have T of j omega is equal to T of S, evaluated at S equals j omega, which is equal to 1 over RC times j omega. And of course, we're interested in the magnitude of the transfer function, or the magnitude of the frequency response, if you will. The magnitude of T of j omega is equal to, let's see, I dropped off a minus sign up here. It's T of j omega is equal to T of S, evaluated at S equals j omega. I've dropped a minus sign. That minus sign, I've dropped it off all the way along there, and there, and there. So now, the magnitude of T of j omega is just the magnitude of the numerator, which is 1, divided by the magnitude of the denominator, which is omega times R times C. And the phase of this transfer function is equal to the phase of the numerator, which is 180 degrees, minus the phase of the denominator, which is 90 degrees. So the phase term then is just equal to a constant 90 degrees. Notice that the magnitude of the transfer function goes to infinity as omega goes to 0, or at DC. So the gain term at DC is effectively infinite. In practical terms, the op-amp is going to saturate if you've got any DC component to the input at all. The capacitor acts as an open circuit for DC, and there's effectively no feedback. With an open circuit here, there's nothing feeding the output back to the input to constrain the output, and the op-amp saturates. That's a problem. We're going to address that in the next video when we talk about, or when to address that, we'll add a capacitor in parallel. We'll add a resistor in parallel with the capacitor to give us a finite DC gain. But using this transfer function, let's just look at the Bode plot. It falls off as 1 over omega. As we've seen in our previous discussion of Bode plots, falling off as 1 over omega corresponds to a straight line with a slope of either with a slope of either minus 20 dB per decade, where a decade corresponds to a multiplying the frequency by 10, or a 10-fold increase in frequency. And similarly, that slope will be negative 6 dB per octave, where the octave represents a doubling of the frequency. So doubling the frequency, we go from, say, 1,000 hertz or 1,000 radians per second to 2,000 radians per second, 4,000, 8,000, 16,000 radians per second. A constant step along the axis when we're doubling corresponds to an octave. On the other hand, when we're going from decade to decade, we're going 10 times. A constant step along the frequency axis represents a 10-fold increase. So we'd be going from 1,000 radians per second to 10,000 radians per second to 100,000 radians per second. The point where the curve, or the slope in this case of the line, where the line intersects the 0 dB point, which corresponds to unity gain, is the frequency 1 over RC. And that's known as the integrator frequency of this circuit.